Good morning, ladies and gentlemen. Thank you very much for joining us this morning. As it has been indicated, I am Princess Masondo, and I'll be facilitating the workshop, which is titled Hypothesis Testing. So in terms of what we're going to cover, there is some introduction to lay a foundation. Then we will look at certain aspects of hypothesis testing, and we will touch briefly on probability, and we will look into sampling distribution, and we will just close by summarizing everything. So in terms of hypothesis testing comes in when you are doing inferential statistics. So where I always like to start is to say that when one is doing a study, in most cases, there is a population that you are interested in studying. So there is something that is occurring within a certain population of interest that is occurring, and you want to measure that thing, or there are certain things that you want to test within a population. So the population will consist of units of interest, which could be people, it could be animals, it could be companies. So it could be the units doesn't necessarily talk to people. When we say units of observations, we're not necessarily talking about people. The population, as I've said, could be, for example, businesses. So that population, you will define it based on what you are interested in studying, but there will be the list, it will have a list of all the units of interest. So if you are interested in SMMEs, then your population will contain the list of SMMEs. If you have further criteria, perhaps it's going to be SMMEs within a certain geographic location, or yes, so if you have a further criteria to delineate this population, you will use them. And then it's going to have a size. So the size talks to the total number of the units that are within this population that you have described. So you are interested in the population, but in most cases you are not able to get to the population because of its size, such that you select a sample. So the sample now becomes your means to the population. So your interest is in the population. You are interested in the population of SMMEs. But then because of the large number of the population, then you select a sample. So the sample is what is assisting you to get to the population. And what you are hoping to do is to take what you would have observed from the sample and you paste it on the population. So we say you make inferences because your interest is in the population. So when you are testing hypotheses, the conclusions that you want to make, you want them to talk to the population, not the sample. The sample, we assume that you will select it such that it's representative of the population. And then what you get from the sample, you actually want to paste it, or you want to make inferences, or you want to make generalizations. So even though you only observed this sample, you want to take what you observe there and you make generalizations. So you generalize what you are seeing from the sample and you generalize it to the entire population. So the sample itself as well will be selected within the population. So the sample will be made up of the units that you would have selected based on the appropriate sample size. So then the sample size will just be the total number of the elements that you would have sampled, you will determine the appropriate sample size, which is not the focus of today's workshop. So very important, you have a population, then you use the sample to get to the population. What is important is also to know that the population, whatever you want to observe from the population, it's fixed. Because if you were to measure the entire population, you would be able to get a fixed number, and that number doesn't vary. It doesn't vary because you've measured everyone. So if I were to want to investigate something about the postgraduate population at UNISA, and MNDs, for instance, if I measure it from all the MNDs, then I would be having the true population value. So if, let's say, I am measuring the average age, so if I get everyone's age and I get an average, I would be having what? The true average age of the UNISA MND population. But if I select a sample and I get the age from the sample as an estimate of the population average age, that one that I will be getting from the sample can vary because it will be dependent on the sample. So if I select the sample, if I take everyone who's attending today as a sample, I will get a certain average. And if tomorrow we have another workshop and we have, it's not gonna be exactly everyone who's here today will be here tomorrow. And we take the average age, so it's gonna vary. So which is leading me to this slide to say that when whatever we are measuring from the sample can vary because it's dependent on the sample that is selected. If I select from everyone who's here, I select 50 and I measure the average age, I'm gonna get a value. If I take those 50 back and I select 50 again and I compute the average age, I'm gonna get a different value to the one that I got the first time. If I do it again, I will also the third time get a different value because each time I sample the sample, the different samples that I'm selecting, I'm using the same approach, the same sample size. However, because it's random, I'm not going to get identical samples. Because the samples are not identical, the averages that I'll be computing for each sample, they will differ. So this is what I'm trying to bring across here to say that different samples will give you different values depending on what you are computing. And it is advised that you the sampling is as sound as possible, you know. The things that we do in inferences, they are based on sound probability sampling techniques, even though we apply them to non-probability sampling techniques. So the sampling has to be sound as possible. Because when we use non-probability sampling approaches, we do lose some of the properties that are required for sound. So we can still make inferences, as many of you would know, even if you don't use probability sampling, you use convenience sampling or non-probability, any other form of non-probability sampling, you can still make inferences, but sometimes you do have limitations as to what you can actually, the generalizations that you can actually make. So we are interested in something that is happening in the population. So the things that we measure from the population, we refer to them as parameters. So going back to my example, if I measure for the weight, or if I measure the age of all the M&D students at UNISA, I'm going to get a parameter because I've measured everyone within the population. So the average that I'll be getting, the average age that I'll be getting will be referred to as a parameter. And it's fixed, as I have said, because if I've measured everyone, even if I measure you again, you will still give me the same age. All of you will give me the same age, and then which will take me to the same average. So in that way, the population, the parameters, they are fixed. They don't vary. The only challenge is that we're not always able to actually measure them. So it's not always possible to actually measure the entire population. And in some cases, it's also not necessary to measure the entire population, which is then why we end up using a sample. So the sample, what we measure from the sample, we refer to whatever we're going to compute will be referred to as a statistic. So the sample will have units of size n. So n is the sample size. So I'm going to be having the units which are from 1 up until n. If my sample size is 100, I'm going to have 100 units, and I'm going to be estimating, or I'm going to be computing the average age from the 100 M&D students if my sample size is 100. And as I've said, what I'm computing from the sample will vary from sample to sample. I've already tried to explain that each time you select a sample from the same population, following the same methodology, because when we're doing probability sampling, it's random, then when you select, each time you select, you get a different sample. I mean, even if we just use a small example of if you take 10 numbers and you put them in a box and you select 5. You select 5 and you put it aside. Let's say those 5, it's learners. You select 5 and then you measure maybe their IQ. You put the 5 back into the box such that you go back to the original. If you select another 5 again, it's not going to be the same 5 as the one that you selected, and you measure the IQ. So I'm trying to illustrate it using a more of a smaller example of when you can actually do the sampling for yourself. If you have 10 learners, as I've said, and you just want to use 5, then you will assign them numbers from 1 to 10, and you draw 5. You can measure the IQ. If you decide to draw another 5, the sampling, the 5 that you select will not necessarily be identical to the first one, such that the average that you'll be computing will vary from sample to sample. So we use statistics. The statistics are used to estimate parameters. So here we say statistics because there are different statistics. So all along I've been using and the average as an example. When it's measured from if we measure the entire population, it's gonna be the parameter, the population average. But once I select a sample and I measure from a sample to estimate the population value, then it becomes a statistic. So we have other examples. I've already used the population mean, where I used the average age. It can be then the population average age. Then on the other side, it's going to be the sample average or the sample mean. And then we can have other parameters. You might be interested in the standard deviation, And then you'd have your sample standard deviation as an estimate. Other parameters would be you are looking at a proportion. So proportion, usually it is a prevalence when you want to know how prevalent something is. So if you want to know prevalence of smoking, prevalence of teenage pregnancy, so that would be, it's a proportion. So you are saying out of a certain population that I'm interested in, how many have this thing that I'm looking at. If it is smoking, how many units within my population smoke? And then we can have another example would be correlation. And then if we estimating it from the sample, it becomes a sample correlation. I think the understanding of this also helps you when you go through statistics material to actually be able to differentiate the different symbols that are being used. And yeah, then it makes more sense when you know that when we talk about a population mean, we also denote it using the mu. But whenever you see X bar, you must know that that is talking to the sample mean. So I think also the symbols themselves assist you to actually be able to understand what is happening within statistics formulas whenever you do encounter them. So in terms of hypothesis testing, as I've said, we are interested in what is something that is occurring within a population. So in the context of hypothesis testing, we will make claims. So a hypothesis then is a claim that we make about one or more populations of interest. In some cases, it's a claim that we make about one population. So if we say the prevalence of depression among M&D students, their population would be 1. It's a population of postgraduate students in the sense of M&Ds. So it's one population, and what we'll be looking at would be the proportion, the prevalence. And it can also then, if we are looking at more than one population, perhaps we could look at the prevalence for undergraduate and then maybe also postgraduate. Perhaps the postgraduate in that case would include the honors and postgraduate diploma. You would decide where you want to put them, under postgraduate or as a separate group. So then that would give you different populations. So the claims that you will be making would then be now about different populations as opposed to one. So the population parameter, so the claim that we make is around the population parameter, which, for example, I use depression to say the claim would be the prevalence. So the population parameter would be a descriptive measure that describes the population. So the prevalence would be describing the population in the form of depression, mental health around there. So it's describing the population, but now specifically in the form of that particular variable of interest. And the hypothesis can be about the nature of the relationship as between different populations. So if we come back, we can make it. So the claims will be coming from you as a researcher, having been informed by the literature or informed by experience, as a person who's working in that particular area. The claims will be informed by some form of evidence, as in maybe there is historical data, there are things that you are observing as you are working in that space, such that you're able to make those claims. And those claims are the ones that you would want to, your study is around. You want to test. Your hypothesis will be around this claim. So you can be making a claim to say the IQ of grade 12 learners is 100. So it's a claim that you could be making, and you want to do, you are doing a study to collect evidence now to be able to test this claim. So the data will come in as you want to use it as evidence that you can use to test the claim that you are making. And as you can see, the other claims when you now have more than one population. And sometimes the claim is about relationship between two things. So it could be, I want to look at the relationship between IQ and malnutrition. So the claim now becomes about two parameters, which one will be malnutrition, and the other one it's going to be IQ. So in hypothesis testing, the data that is collected is used as evidence, or the secondary data that is used as evidence. So even the secondary data, it would have been collected, but not by you, or not for primarily for your study, but you can use it as evidence to test these claims. So you would have, once you make a claim, then in hypothesis testing, you would construct them in the form of two suppositions. So once you have a claim that you are coming with, and then you would convert it into two opposing assumptions or hypotheses, which we refer to as the null hypothesis and the alternate hypothesis. And then the two hypotheses, they are mutually exclusive, meaning they don't overlap. They don't overlap and exhaustive, so that if one is true to the exclusion of the other. And as I've said, that you collect data, whether it's primary data or secondary data, it is collected, it's analyzed, and it is to be used as evidence as to whether now which of the two hypotheses is true and which one is false. So the data that you collect, you want to use it as evidence to now know whether you which hypothesis to support and which one is not supported. So the steps that I've put here are just all the steps that you would undertake until you get to make a decision about whether which hypothesis. So the first thing you'd have to, now in the context of, now we are now bringing it to the statistics, you state the null hypothesis and the alternative hypothesis. And then you state the criteria for a decision to say, when are you going to reject and when do you not reject? So I'm gonna unpack them based on how it is listed. So we will, as we proceed, we will look at the null hypothesis, the alternate hypothesis. Then we'll look at bullet number 2, which is setting a criteria. We look into alpha. What does alpha mean? And then we will talk about the test statistic, the p-value. And from the p-value, you can then, so you can see here in bullet number 2, you set a criteria which will say, I reject H0 represents the null hypothesis, reject H0 when alpha is this much. So if you see, so that's the criteria. So once you now have all the elements, the last decision would be now to say, I've computed the p-value, and then what is the p-value of the p-value? Is it less than the alpha that I would have set? So as I've said, I'm going to look at those points and unpack them. So first you set the null hypothesis and the alternate hypothesis. So you came with a claim but now you convert the claim and you put it in the form of a null hypothesis and the alternate hypothesis for now. When you want to do a statistical test, you need to take that claim that you came with and formulate it in the form of a null and alternate hypothesis. So the null hypothesis, I've said there are two then hypotheses. The null hypothesis, which we denote by H0, it states the assumption or the supposition to be tested. It is about population parameter or one population parameter, for example, the population mean. So if we go back to the initial examples that I made, they were around the population mean. And I used one example previously, as we spoke about IQ, average IQ. So the hypothesis would be about the average IQ of the population. You are hypothesizing that the average IQ is a certain value. And when we, in terms of the null hypothesis, we assume that the null hypothesis is true. So whatever the null hypothesis is, we assume that it is true. So if you hypothesize that the average IQ of grade 12 learners is 100, we assume it is true. That's where we start from, and we will now use our data as evidence to either reject it or we say we don't have enough evidence to reject it. So we can say, in terms of the null hypothesis, you can say that it's equals to a certain value, which is the example that I've used. I've said that the IQ, the average IQ is equals to 100. That would be the null hypothesis. You say it's equals to a certain value. If you are talking about prevalence, that is why when we even when we do the sample size, we ask you, what do you think the value is, an estimate. Yeah. But here in the null hypothesis, it's going to be this value that you found from your the data that you would have collected, maybe not necessarily in a formal way, but you do have some sense of a certain value. And sometimes the value will be, as I said, informed by literature, right? If the example that I'm going to use at the end, if we talk about birth weight, there is literature or there is evidence that will tell you that what is the average birth weight for a healthy baby. What is the average birth weight? Not to say that, when we talk average, I think we all understand it doesn't mean that all the babies will be 3.5 if the average is 3.5. But when we look at the distribution of babies and we look at the birth weight, it's going to be around 3.5. And then perhaps if you suspect that children in a certain village, they are actually, you are getting evidence, you're getting a sense that they are born underweight, meaning that you're seeing a trend whereby the babies are below this 3.5, which the literature suggests, and also as an from your experience, to be true that on average, a healthy baby is around 3.5. But you see maybe in a certain village that babies that are being born, there's this trend, they are maybe below 3 kg. You're seeing a certain trend, and then you do a study, then the certain value in that case will be what is standard. And you would want now to see if for this population, if the average birth weight is standard. So then the certain value will be maybe 3.5, if 3.5 is what is standard or the norm. So yeah, and the other examples, it can be that the hypothesis will be about that there's no difference. So if we are talking about two parameters or two populations, when we state the null hypothesis, we state the opposite of what you want to show as a researcher. So if you want to show that learners who are going to quintile 1 and you want to compare them to those who are from quintile 5 with regards to something, then you will say in terms of the null hypothesis. So as a researcher, you'd be doing the study because you've observed that perhaps there's a difference with regards to the variable. When you are coming from this area, this is what you're observing when you compare to learners who are coming from a certain area or the different quintiles, if you use the South African context. So, but when you state it as a null hypothesis, you will say there's no difference. So as a null hypothesis, you will say the two groups don't differ. Or if you are looking at relationships, if we go back to my other example about malnutrition and IQ, where you've observed that it seems like malnutrition is affecting the IQ level or maybe performance, and then obviously you are sensing that the children who are experiencing malnutrition, their performance is lower compared to those who are not experiencing it. So then you want to be looking at a relationship between those two variables. Then as a null hypothesis, you will say there is no relationship. So the null hypothesis, how you state it, it's usually opposite to what you want to show as a researcher. What you want to show as a researcher is usually contained in the alternate hypothesis, as you will see here. So the alternate hypothesis would be the opposite of the null hypothesis. So in statistical, when we do hypothesis testing, we have, so you take the claim that you came with, that you picked up from wherever, then you state it in the form of the null and the alternate hypothesis. The null hypothesis, as I say, it's going to be silent. It's going to be the opposite of what you want to show. So you will be saying there's no relationship between malnutrition and performance. But when you come to the alternate hypothesis, it's the opposite of the null hypothesis. So if the null hypothesis is saying that there is no relationship between malnutrition and performance, the alternate hypothesis will then say there is a relationship, which is what you as a researcher believe to be true. So the last bullet, the alternate hypothesis usually captures what the researcher believes to be true, which is the opposite of the null hypothesis. Because, for example, if you think about interventions, if you think about a new treatment, you'd only advocate for it or want to test it because you believe that it's better than the existing. Otherwise, there wouldn't be any value in introducing a new teaching method, a new treatment, if you don't believe it's better than what is currently existing. But the null hypothesis will say that the new treatment and what is existing, they are the same. But you as a researcher, you are actually doing the study because you believe that the new treatment can give better results compared to the existing or the standard. So the alternate hypothesis captures what the researcher believes to be true, which is really what the researcher wants to gather evidence, hoping the researcher is hoping that the data collected will present evidence to reject the null hypothesis. So in statistical test, in hypothesis testing, we want to reject the null hypothesis because the null hypothesis says it doesn't matter. The old treatment and the new treatment are the same. We want to reject it. And we use the collected data as evidence. So the alternate hypothesis is what is considered to be wrong about the null hypothesis. So with the alternate hypothesis, I think it's important to know that can be stated in more than one way. One way will be to say, if we're talking about a new treatment and an old treatment, one way we just say they are not the same. That would be the alternate. The alternate says they are not the same, but it doesn't really say this one is better. It just says they are not the same, which means when we do the test, we will look at both sides, the less and the more. Then the other way to put the alternate hypothesis is if it's got a direction. So you will say the average performance of learners who were taught using the new teaching method is higher than the average of those who were taught using a standard approach. So that one would have a greater, a less than. The other way would just say it's not equals to. The second way will either say one is greater or the other one is less. Yeah. So I've already said that then the alternate hypothesis will say there is a difference, right? Or it will say there is a relationship. So, for example, if we toss a fair coin, if we toss a fair coin, you can either have a head or a tail. And if we assume that the coin is fair, as I've said, it's not biased, then we expect the probability of getting a head, that it lands on a head, will be the same as the probability that it lands on a tail. So our null hypothesis would be saying that the coin is unbiased, meaning the probability of getting a head is the same as the probability of getting a tail. And then the alternate hypothesis will oppose what the null hypothesis said. So then you can collect data as evidence. So you can take the coin and you can do many trials and collect the data and then be able to say whether this null hypothesis should be rejected or not. Perhaps the coin has what can we say, has a defect. Yes, so perhaps the coin has a defect such that, yes, we assume it's fair, but maybe the data will prove us. So perhaps you are doing the study because you suspect that there are defects. And then the data that you'd be collecting as you do the trials by tossing the coins will now be presented as evidence to say, are we seeing that the probability of getting a head and a tail, or are we seeing that there is more of a weight to a certain side of the coin? Then the other example in terms of how you can put your hypothesis. So this one talks to what I've alluded to, that as a researcher, you would be doing a study about a new drug because you believe that this drug would perform better than the existing one. So then you can measure the blood pressure before. So the hypothesis will also depend on the test that is appropriate for what you want to do. So you can see here, even though we are talking about an average, the mean, we are talking about the mean here, but in the context of what we want to show here, the null hypothesis now talks about the average blood pressure before and the average blood pressure after the drug has been administered or the new treatment has been administered. The null hypothesis will then say that the average blood pressure before would be the same as after. And as I've said, then the alternate will oppose that, because the alternate captures what you want to show. So if in your document you want to capture, or even if you are not capturing them inside your proposal, but you are capturing them in maybe a separate working document where you are capturing your variables and you are unpacking them, the easiest way to approach this would be to say, what do I want to show as a researcher? Then that you can write as your alternate hypothesis. And then you can take the opposite of that and make it your null hypothesis. So you can start by putting, so sometimes you will be saying that I want to see if there's a relationship between X and Y. So that the relationship between X and Y, you can put it as your alternate hypothesis. And then you can now translate it into the null and say, then because this is what I want to look at, then the null hypothesis will say there is no relationship, because the null hypothesis is what I want to reject. Yeah, so, and it helps, especially, for example, now that you know that I'm looking at before and I'm looking at after, in your mind also, you will now, when you look for statistical tests in your reading, you know that, that it has to talk to before and after. So once you've captured them here, it also assists you to take it further to data analysis. When you read, when you now see which test is appropriate, the null hypothesis and your alternate, when you've put them here in, you see what you actually want to test. And then you can look at tests that are applicable for that. So generically, hypothesis testing is not a formal proof, yes, but it's more about the evidence that is presented. So we usually liken it to a court case, that in a court case scenario, everything is based on what? On evidence. And in this case, we use the p-value as our evidence, especially if you're going to be using a software. It's gonna, at the end, it's gonna compute the p-value for you. So it's based, even with hypothesis testing, it's based on the evidence presented. Based on the evidence presented. So just to summarize, the null hypothesis is the hypothesis that we want to test. So we are interested in testing the null hypothesis. The null hypothesis that says there is no difference, or that says the average population is a particular value, or there is no relationship. So you must look for a no in the null hypothesis. There must be a negation, a no, in your null hypothesis. Yeah, so the null hypothesis, it's the hypothesis of interest. So also very important, if you're going to write it down, maybe you want to use symbols, it's about the population. And then it means that you have to use the symbols that talk to the population. So for example, the null hypothesis here is saying X bar. So it cannot say X bar, because X bar is a statistic, it's a sample mean. So the null hypothesis, in terms of the symbols, also it's about the population parameters. So it must say mu if you are talking about the mean. It doesn't favor any group, as I've said, it's silent. So you must look for the no there. So our starting point is we assume that the null hypothesis is true. So when we are doing our testing, we assume that the null hypothesis is true. And we want to use probability theory and the data to see if we have enough evidence to reject it. Because you as a researcher, you are interested in the alternate, which says that there's a difference or there's a relationship. So you are hoping that the data presented can show evidence to reject the null hypothesis. So so then because we're using a sample, there is always that risk that the inferences that we make, remember, even though we are observing a sample, our inferences are about what? The population. We are taking what we're getting from the sample and we are pasting it on the population. So picking it up on the last bullet, that there is that possibility that the inferences that we are making, they're incorrect because it's based on evidence, which leads us to the errors which we can commit in hypothesis testing. So there are two errors that we can potentially commit, type 1 and type 2 error. So if we go back to the courtroom situation, we say that everything is based on what? On evidence. If there's someone who's on trial, the judge has to decide whether they are guilty or not guilty, even though the person might be innocent or they might be guilty. This is important also to understand because it helps you to understand it in the context of your statistical testing, that if you can have a mind that when someone goes to court, the truth is already there. The truth of whether they have committed the particular crime or not, whether they are guilty or not, is there. This person, as they appear, they have either committed or not. The truth is there, known by them, maybe known by other people as well, but it is there. The truth of whether they've done this or they haven't. But now when they appear in court, the decisions will be based on what? The evidence that is presented. And as the basis will be that the person is assumed to be innocent, right? There is a favored assumption. They are assumed to be innocent. So that's the premise. That's where we start from. We start by saying you are innocent. And then it's now up to the evidence to sway this premise, to say the evidence presented says we must reject this assumption and say you are guilty. So there's an initial bias. So the same way with us in hypothesis testing, I've said we assume that the null hypothesis is what is true. That's where also our premise is. We assume the null hypothesis is true. Here we assume the person is innocent. So the evidence, obviously, in a court situation, it has to convince beyond reasonable doubt, right? And then the defendant would be declared guilty. So in this setup, there are mistakes which can be made. Remember, we say there are mistakes because the truth is there. The truth of whether this person has committed this offense or not is there. Then the judge, the court can make two mistakes, which we can also say it's type 1 and type 2 error. So the judge can decide that the person is guilty while they're in actual fact innocent. So it's then when they reject that initial assumption of innocence. So they reject it. Their rejection is based on the evidence, right? But they might reject the assumption of innocence, while in actual fact, the person is innocent. But the evidence was presented in such a way that they concluded that this person is not innocent. So they reject that the premise that the assumption of innocence. So they would be committing an error because this person is innocent, but they are rejecting that assumption only based on what? The evidence. On the other hand, they might not reject that assumption of innocence. So the judge decides that the defendant is innocent while they are in actual fact guilty. So they don't reject the assumption of innocence, while in actual fact this person has committed the crime. So, but what you need to take out of this is that it will be based on the evidence presented. That is why you can appeal, and maybe it can be taken to another court, and you find that the decision is different, right? You come out with a different decision. Perhaps the evidence would be presented better also because the judges are people in terms of how they interpret what is being presented. They're not going to interpret it the same way. And I suppose they're applying different, maybe same principles, but maybe interpreting them differently. Maybe someone with a legal background would can add more to that. But yeah, we are aware that you can take the decision of the court on appeal and take it to another court, and sometimes it will come back with the same. Sometimes you'll get a different verdict. So it's all about the evidence. So in hypothesis testing, we let so there is a type 1 error and a type 2 error. So we say the type 1 error is if they decide that you are guilty, while in actual fact you are innocent. Then the probability of committing that error, we say it's alpha. So whenever you see alpha, alpha is the probability of for type 1 error. Alpha denotes the probability of a type 1 error. I will bring it back to our hypothesis testing, but for the example that we are using, the type 1 error will be the judge decides that the person is guilty, while in actual fact they are innocent. So it's when they actually reject that null hypothesis of innocence, while the person is in actual fact innocent. So we want alpha to be small. The type 1 error, we want it to be small. And in hypothesis testing, we set the type 1 error. We say this is the amount of error we can accept. Then we also have the type 2 error, which that would happen if the judge decides the defendant is innocent while they're actually guilty. So the probability of committing that error, we say it is beta. So beta denotes the probability of committing a type 2 error. And similarly, we also want beta to be small. So just to summarize, so going back to this analogy we are using, that there is the actual truth, which is this part. There is the actual truth. So there is the truth, which is the truth of whether this person has committed the offense, they are guilty or they are innocent. And then on the one side, we have the decision that is based on the evidence. So if the court says you are guilty while you are innocent, it's going to be a mistake, right? It will be a type 1. If the court says you are guilty and you are actually guilty, obviously, that would be perfect. It's what we want. And if the court says you are innocent when you are in actual fact innocent, that is what we want. And if it says you are innocent while you are actually guilty, that would also be a mistake. Those are the things that we have to live with. There are the possibilities in a courtroom situation. In terms of the mistakes, I just want you to comment in the chat box to say which one would be more of a severe mistake to make, or are they equally important, or do they have the same weight, the two mistakes, according to your own understanding? Maybe you can comment in the chat box. It's a yes or no. You can maybe elaborate and say the first mistake, if they say you are guilty while you are innocent, maybe it's more of a less severe mistake compared to when they say you are innocent while in actual fact you are guilty. Which one would be more of a severe mistake, or are they equally, do they have the same weight? Maybe I'll just pause for a minute so that you can think about it and attempt to provide an answer there, and then we can just wrap it up. Tony, maybe you can, once if they are coming out, you can, once we have a few responses, just a few, maybe you can say them out.
Thanks.
Okay. So yeah, I would maybe understand where you are coming from. I suppose with this one, it depends on which side you are, From the side of the court, the premise that we are coming from is that you are innocent. And then it's based on the evidence that we move from that position as the court to the you are guilty. The court wouldn't want to put people who are innocent, punish people who are innocent. If we're looking at it from the court's perspective, they wouldn't want to punish people who are innocent. They would rather let someone who is guilty. So in this context, coming from the court side, you wouldn't want to punish there's justice. You wouldn't want to punish people who as I've said, who are innocent. So more for the court, the more of the mistake they can live with is the other one where they say you are declared to be innocent while you are actually guilty, but not to say you are guilty while in actual fact you are innocent. That's why people can sue and some people, while they are under arrest, they gather evidence and they are able to show that the court erred, and they can they can they sue so that they can be compensated for whatever they went through. Yes, so in that context, the court would rather say you are. So that's why we talk about that, even though I'm not in the legal space, but they talk about beyond reasonable doubt. So if there is some element of, it's not beyond reasonable doubt, then they will let you rather say you innocent. So the evidence has to be beyond a reasonable doubt. Otherwise, they rather say you are innocent, as I've said. So, yeah. But I suppose if you are maybe the family of the victim, and the victim, you'd be happy because you believe the accused is actually guilty. So you would be happy if they just say the person is guilty, even if they are not guilty, but in your eyes, based on the evidence that you have, this person is guilty. So you will be happy if the court says they are guilty, even if they're innocent, because in your eyes and based on what you know, which is the evidence, you know them to be guilty. So yeah, the other one wouldn't be happy. But in terms of a just system, they'd rather let you go than punish you for what you didn't do. So if we bring it to our context, we have a type 1, we have a type 2 error. I've said the type 1, so the probability of committing a type 1 error. So you mustn't see alpha as a type 1 error. No, it's the probability of committing a type 1 error. It measures that the magnitude of the likelihood of committing a type 1 error. So it's a measure of the likelihood of committing a type 1 error. It's a probability. Alpha is not type 1 error, but it's probability of committing type 1 error. So we say our null hypothesis is silent. So, for example, our null hypothesis will say that the new treatment and the old treatment are the same. And I've said that we assume the null hypothesis is true and we want to actually reject it. I've said that in hypothesis testing, it's all about the null hypothesis. So when we commit a type 1 error, it's when we reject the null hypothesis when it is true. So a type 1 error, we commit it by rejecting the null hypothesis when it's true. When it's true, it says, for example, it says the two treatments are the same. When we reject it, we are saying they are not the same. So a type 1 error is if we say the two treatments are different, when in actual fact, they are not different. So, and then on the other hand, we will have type 2 error, which will be when we don't reject the null hypothesis, when it is false. So when the null hypothesis is true, it's when it's saying that it says the two treatments are the same. When we don't reject it, when it's actually false. So I think to connect it with the courtroom analogy is to say that even in statistical testing, we are saying we're using sample data as evidence, but we are saying that if we had the opportunity to collect data from the entire population, we would have a true value. We would be able to say whether this, if we had the opportunity to give the treatment to all the patients, we would be able to say whether the two treatments are the same or they differ. So the truth is there. It's just that we're not able to get to it because of the size of the population. So when we say when H naught is true, we are saying that when in actual fact it is true in a sense that if we were to gather more evidence by collecting from the entire population, we would find that it's true. So look at it in that way, that we have the evidence, which is the sample data, but we also have the truth and what is not the truth as to whether this treatment is effective or not. So we can reject the null hypothesis, meaning we are saying the treatment, the old and the new treatments are not the same, when in actual fact they are the same. On the other hand is when we don't reject the null hypothesis, when we don't reject it, when it is false. And in terms of the type 1 error, it's usually set to be 0.05. So I've indicated that type 1 error, because it talks about the amount of error that we are willing to accept, we can set it, and it's usually set at 5% or 0.01. In other cases, it is set to be lower, 0.01, because if you think about the type 1 error, if you look at a situation where you are looking at a new treatment, an old treatment. You don't really want to implement a treatment that is not effective, that is gonna cost you money. So in certain settings, you would want to make your type 1 error to be much smaller, and hence the 1%. So the chance of mistakenly declaring a difference, because when we reject the null hypothesis, we are saying that there is a difference, a significant difference between the two treatments. So we want that chance to be not more than 5% or 1% if we are using a 1%. And in terms of the type 2 error, the type 2 error is used for when we do sample size estimation, because we look at the opposite or the complement of the type 2 error, which we say is the power, which is the probability that the effect will be detected, meaning that you reject H naught when it is false, meaning that you say the treatment is effective when it's actually effective. When we reject H naught, we are saying the two treatments are not the same. So we want to reject H naught when it is false. Then that probability is regarded, it is regarded as the power, which is the complement of the type 2 error. Yes, so I've said we call it the power of a test, which is we reject H naught when it is false. So the power of a test, because it's a statistical test, the power of a test to actually pick up differences when they are actually there. Usually we set the power to be at 0.8. So we've looked at the null and the alternate hypothesis, which was the first bullet when I was talking about the steps. We've now looked at, you set a criteria. So you say, when do we reject the null hypothesis? Now that we know how to put the null hypothesis, then we moved on to say the criteria. When do you reject the null hypothesis? And we say that we use the type 1 error, alpha, probability of a type 1 error, which is the probability that it's an error, right? It's a type 1 error, meaning that we reject the null hypothesis when it is true. We want to reject the null hypothesis when it is what? When it's false. So we set it at alpha. So if we already set the criteria, we've done bullet 2. So we are saying that we will reject the null hypothesis when the p-value which we will get to is less than the type 1 error. So the p-value is a measure as well. Is a measure of it measures the likelihood that the differences or the observed outcome, the outcome that we would be observing from the sample data is by chance. When we say by chance, it means that it doesn't represent the population. It's just so happened that we selected a sample that is giving this the outcome, but it is by chance. So we want the probability that the outcome, because I think you will see, or you will see when you do analysis, if you are comparing two treatments, isn't it, you will give one group a new treatment and the other ones, they will continue on the standard treatment. So if it's treatment for whatever, then at the end, let's say it's a new teaching approach, then at the end we're gonna compare the average performance for these learners who are on this new teaching approach and the other learners who are on the old teaching approach, and you'll be comparing the average. Obviously, they are being taught the same topic. They are assessed the same way. It's just that the teaching approach is different. The average that you will be getting is not going to be the same from this group and the other group. But what we want to know is this average, this is the outcome. That's what I'm talking about. what probability, what is the probability that this outcome is by chance? By chance, it means it doesn't represent the true population. It just so happened that our sample is giving this outcome. So we also want to quantify the probability that this outcome that we are seeing from the data is by chance. And we say we reject the null hypothesis when this probability that the outcome is by chance is very small, because we don't want to make generalizations when the probability that this outcome is by chance is high. We want the probability that the outcome is by chance to be small. How small? Then we use our alpha. It must be less than the type 1 error. Yeah. So this is a summary for us. There is the null hypothesis, which the null hypothesis, there is a reality about it as to whether it's true, it's false. Then there is the other side of the evidence that is presented by the data. So based on the evidence that is presented by the data, we make a decision. So we can reject the null hypothesis when in actual fact it's true. Then that would be a type 1 error. And then if we reject it when it's false, then we are happy. And the other error I've said we can commit if we don't reject it when it's actually false. If we reject it, if we don't reject it when it's true, it's fine. Because when it's true, we don't want to reject it. We only want to reject it when it's false. So this just summarizes the notion around the type 1 error and the type 2 error. Then there are probabilities for committing these errors. Alpha captures the probability of committing a type 1 error. Beta captures the probability of committing a type 2 error. And then the complement of beta gives us the power. So I've already made reference to the p-value. So because in the second bullet, we use alpha and we use the p-value. So our the criteria that we set to reject the null hypothesis, we say we reject the null hypothesis when the p-value is less than the alpha, right? That's what I've put there. And we said that alpha is usually set at 0.05, sometimes 0.01, and we've defined what alpha is. Then the other aspect to the bullet is the p-value. So the p-value is the probability of observing the sample data under the assumption that the null hypothesis is true. So the assumption that the null, if we go back to my example, the assumption that the null hypothesis is true leads you to, if we look at this, it leads you to the middle. If we go back to my example about birth weight, yes, if we use my example of birth weight, whereby we hypothesize that the birth weight should be 3.5. So most of the values will be, the sample means would be close to the middle, which would be the truth. Remember, the null hypothesis is based on the population. You can see here, it's what is seen here is mu. Mu will be here. And we are saying that our mu is 3.5. So the values would be close to the central. And then we have the other cases where we're going to have extremes on the left and on the right. So the extremes will be those values that are far from 3.5, right? 3.5 is here. The extreme values will be those values that are far from 3.5. If we assume that indeed our the data that we have collected, the average is 3.5. Then when you look at the weights, you will have some extremes, as I've said, which will be far from the 3.5. Some will be lower, extremely lower, and some will be extremely higher than 3.5. And then we have those who will be close to 3.5. That is if the sample data, indeed, the average is, the mean is 3.5. We'll find that we don't have a lot of values on the sides. We have a lot of values close to this hypothesized value. So then you can see the p-value as a cutoff point below which we will view the statistic from our data as not compatible with the null hypothesis. Yes, what is compatible with the null hypothesis is for us to be getting a lot of our values close here and very few in the extreme sides. So what we then say, the p-values that are above alpha will be viewed as the statistic from our data being compatible with the null hypothesis. So we are looking for small p-values. Why? Because if the p-value, as I've said, is, if in simple terms, you have to see it as that it quantifies the probability that the outcome is by chance. If we have a high probability that the outcome is by chance, then it means that what this outcome doesn't really represent what is happening. And you will see that if the outcome is by chance, this area will be bigger. The extremes will be bigger because it means that we will have a lot of observations in the extreme. So the shaded area will be bigger. And if the shaded area is smaller, then it's fine because it means that most of the values are close to this hypothesized value. Most of the values are close to the population mean. But if this area is bigger, then we have a lot of extremes. And then the lot of extremes are deviating now from saying that we're supposed to have most of our observations in the center. So the other thing is that what we need to know is that the p-value doesn't measure the effect. So it just tells us the extent to which the outcome that we are seeing is by chance. And if the probability that the outcome that we are seeing is by chance is high, obviously we can't generalize based on an outcome that is has a high probability of being by chance. But even when we have a small p-value and we reject the null hypothesis, then it doesn't mean that, doesn't talk about the effect or the size of the difference observed. So if we go back to my example about high blood pressure, if we find that the new treatment and the old treatment, they differ significantly from each other, meaning that we got a small p-value, then it doesn't talk about the effect. So it doesn't necessarily say that, yes, the results are saying that there's a significant difference between the two treatments, but it's not really quantifying the size of the difference. So the difference could be very small. So then for you to be able to say whether the difference is significant or not, now when we say significant, I'm talking about practical significance or clinical significance, to say that if these two treatments in terms of high blood pressure, they differ by only 2 units, 5 units, and maybe this treatment is expensive. So you have to look at now the context to say, in the context of high blood pressure, if it drops just by 2 units, is it worth it? Or do we start to say we are happy or when it drops by 15 units or by 20 units? So yeah, I hope I make sense there. So here is the example of the p-value. So if we toss a coin 100 times and we have a null hypothesis that says that if it's fair, it's gonna land on the tail 5 times, and then it's gonna land on heads 50 times because we are tossing it 100 times. So the probability of getting the heads and the tails is the same. Then the alternate will say it's not balanced. So if, for example, the coin lands on 95 heads out of the 100 tosses, then in this case, the probability, the p-value will be the probability of getting the extremes, which will be 95, 96, 97, 98, 99 for 100 heads. And then the other extreme, which will be the probability of getting a 0, 1, 2, 3, 4, 5. This is if we assume that the null hypothesis is true. If we assume that it is balanced, then the p-value, we will be computing it on the probability of getting 95, 97, 98, 99, or everything as heads. And I think if you come back here, this will be the extreme. Here, if we look at the line as the number of heads, it's going from the small to the high. Here, starting by getting 0 heads, 1, 2, 3, 4, 5, up until 100. The 0 side will be the one side of the extreme. The 100 side will be the one side of the extreme. And yeah, if we say that's what we say in here, that so these are the extremes. That is if the coin, remember, we're going to be tossing it 50 times and we're going to have outcomes. And this are if we use this outcome, 95 out of the 100 tosses, then we have to look at this probability and the other extreme. That's if we assume the null hypothesis is true, if we assume that it's balanced, that the probability of landing on a head and on a tail are the same, then the p-value will be now looking at the extreme based on the data, which gave us 95 out of 100 tosses. So yeah, I'm now already using the concept of probability, but it is a measure of the likelihood of event occurrence. So I've spoken about the p-value being a probability. I've spoken about alpha being a probability. So it measures the likelihood of occurrence. So in the form of alpha being a type 1 error, alpha being probability of type 1 error, it measures the likelihood of us having a type 1 error. If we go back to the p-value, we also said it measures now, it gives us the measure of the probability that the outcome that we will be seeing is by chance. Obviously, the outcome, it's the outcome of our analysis, our test, that it is by chance. So some of the properties of a p-value, which will also help you when you look at not of the p-value of probability, whenever something is referred to as a probability, these properties will help you to know in your mind what you are expecting. So it's going to be a value between 0 and 1. So the whatever probability, whether it's probability of type 1 error, the probability that the outcome is by chance, which is the p-value, whatever probability, whether it's a probability of type 2 error, whenever we talk about a probability, you must be in your mind thinking about a number that is between 0 and 1. Inclusive. Inclusive means that it can be 0, right? It can be 1. So when it is 0, it means it's impossible for that event to occur. Then when it is 1, it means that the event will occur with certainty. So the probability is, we use it to make predictions about the likelihood of occurrence of events. So if we come back here, we see that we are curbing the probability of type 1 error to be 0.05. And then we also say that we don't want a high probability of the outcome being by chance. So in our hypothesis testing, we compute that probability of our outcome being by chance, and then we compare it with the standard that we have set. So just to reinforce the probability. So we've said it is probability, it quantifies the likelihood of an event occurring or observing a certain outcome, and we use it for predictions. So if you roll a die just to see the what probability means, you can think about when you roll a die that one die has possible 6 outcomes, right? If I roll it, can either land on a head, a 1, a 2, a 3, a 4, a 5, or a 6. So I have 6 possible outcomes. So if I roll a die, I know that the probability that it lands on 1, it's going to be 1 out of all the possible outcomes. So I have 6 possible outcomes. So the probability will be 1/6. And then the probability that it lands on a 6 as well, 6 is just one outcome, which out of how many? 6 possible outcomes. So then the probability will be 1/6. And then if we look at 2 balanced dice, so if we now look at, there I rolled 1, here I am rolling 2 dice. I roll them. So when they land, I have 2 numbers, right? When they land, I will be having 2 numbers, one number appearing on the first die, the other number appearing on the second die. So my question is, what is the probability that the sum, when I add the 2 numbers, the one that is appearing on the first die and the one that is appearing on the second die, what is the probability that when I add those 2 numbers, I get a 1? And then the second question, which you can answer in the chat box, is same. I have those 2 dice, right? They will land, each one will land on a number between 1 and 6. If I sum, what is the probability that if I sum the 2, I get 12 or something less than 12? I either get 12 or a number less than 12. What is that probability? And then what is the probability that in the first one that the sum, when I add the 2, I get a 1. I'll also give the answer in A and B, so they can give the answers for A and say, A, this is the probability. For B, this is the probability. I'll give them a second also for that. And I think we can, when I finish the section on probability, we can take a break. So the question is, you have 2 balanced dice. So 2 balanced dice, you have 2. If you roll them, they all will land at a number between 1 and 6 because those are the possible numbers. So then once they've landed, you're gonna have two numbers, one appearing on the one die, the other number will appear on the second die. So what my question is, what is the probability that, depending, it doesn't matter what they land on, what is the probability that the sum will be 1? If you add the numbers, what is the probability that you will get a sum of 1? What is that probability? So you give an answer. Then the B asks, what is the probability that the sum, remember, if I toss it, mine might land on different numbers than when Tony is tossing it. But the question is still the same. What is the probability that when I sum the numbers that my two dice landed on, what is the probability that the two numbers, when I add them, I'm going to get a 1? Then same, what is the probability that when Tony adds the numbers that are reflected on his two dice, he's getting a total of 1? Then the second one is, what is the probability that when I sum those numbers, I get a number that is either 12 or less than 12? Any attempts?
Yes, we have anonymous saying A equals to 0, B equals to 1. Kenneth, B is 12, answer is 2 over 12. That's 0.17.
Okay, so the correct answer is the one from anonymous. Okay.
Okay, there's another anonymous 1 over 6, which goes to 0.167.
Yes.
Thanks.
So thank you very much. Thank you for engaging and responding. Obviously, when you write it and you think about it, you are also interrogating how you are understanding this. So the correct answer is the first one that was provided, that I have 2. Remember, the possible numbers on each can be, they range from 1 to 6. So on both of them, I can never have a sum that is above 1, right? If I add them up, because the smallest number I can have is 1 on each. So I can never have a sum that is 1. I could have a sum that is 1 if one of the dice had a 0, possibly. Then such that maybe in one occasion it can land on a 0, on one occasion a 1, and then when I add them, I get a 1. So it's not possible that when I sum, I get a 1. I hope it's clear now that the answer is provided. It's not possible because the smallest number on both of them is 1. So if I sum, the smallest total I can get is what? Is 2. So the probability that the sum is 1 is going to be 0. So this is the outcome. The outcome that we are looking at is, if I sum both of them, I get a 1. It's not possible. So that's why we say the probability is 0. Then if we go to the B part, the probability that, so maybe other people, okay, I've already said it's the correct answer is the one by anonymous. So the probability that the sum is 12 or less is 1. Because remember here, we said that the probability that an event occurs with certainty, when an event can occur with certainty, then that probability is going to be what? 1. Which is the case here. If I sum, it doesn't matter the two numbers. I will always get a sum that is less than 12 or equals to 12. I will get a 12 if both of them are landing on a 6, which is the maximum. So the probability that the sum is 12 or less is 1. I will always get something that is less than 12 or is equals to 12. I hope it's clear. So in what we were looking at here, the outcomes were like kind of discrete here. and which is the formula that we use when we have discrete variables. It's the total number of possible events divided by the number of events favoring. So if we went back to the first example, if we roll a dice, one die, then the probability of getting a 1 is gonna be 1. It's gonna be the numerator, which is the number of events favoring. So it's gonna be, in this case, I said that it lands on 1. And then over the total number of possible events. The number of possible events in that example, we only have 6. Can either land on a 1, a 2, a 3, a 4, a 5, or a 6, which gives us, so you can see here, it's A, so divided by A plus the number of events not favoring A. So 1 will be that landing on a 1, and then the 5 will be the case where it lands on 2, 3, 4, 5, 6, which is the number of events not favoring A, which is when it doesn't land on 1 in my example. And then the example here, this is the other example that you can attempt, that there are 20 people who test positive. So we use data to predict. We say probability is about prediction. So we know that we have 20 people who have tested positive. These people are coming from a population of 200,000 people. So we have 200,000 people, and out of those 200,000 people, 20 people tested positive. So now we want to know, what is the probability that if we select a person at random, right? This is the data. We know that we had 20 people. So now, for future, what is the probability that if we select a person at random, they will test positive? So what is the probability that if I just select someone out of these 200 people, they will test positive? You have to look at, you compute it using this formula here, right? So we say the number of events favoring A is 20, right? Then the number of events favoring A, which is testing positive, and then the number of events not favoring A. So maybe someone can attempt it, and then we can wrap this one and maybe go on a break.
We have anonymous, and it's saying 0.0001.
Okay, we'll go with their answer. Yes, so we say that if we follow this, what is favoring is 20 people tested positive, right? And then it means 1998 didn't test positive, right? So if you just take 20 divided by this total obviously includes everyone. If they say 20 people tested positive, it means the other out of this 200,000 did not test positive, which is the part that is not favoring. So I broke it down so that you can see. So the probability that if we select someone that they will come up positive is very low, which is 1 in 10,000. So 0.01% or 0.001. I hope you just get the idea that you look at the outcome of interest, and then you look at the possible outcomes or possible events. That would be what you are dividing with. I think maybe this one makes it clear that 20 is those who tested positive. Then we have those who didn't test positive. And then those who tested positive and those who didn't test positive gives you your total possible outcomes or possible events. And then the one that is favored is the positive, which is 20. So just to summarize, so in terms of discrete variables, we have what we call the probability mass function. which gives us a description of the possible outcomes and their probability for some a discrete random variable. The probability that a discrete random variable takes x on is exactly equals to a particular value. That is the probability that I land on, I get 3 heads, is denoted by fx, and it's called the probability mass function. I'm gonna look at the example and then we close this. So we still discrete. So if we toss a coin twice, right? We are tossing it twice. And then if we want to look at the probability of getting heads, so I can get 0, 1, or 2 heads. Why? Because I can, if I toss it, it's either I'm going to be having a head and a head, right? The first time it's a head, the second time it's a head. These are the possible outcomes. Or the first time it lands on a head, and then the second toss lands on a tail. Or my first toss will be a tail, and the second toss will also be a tail. These are the possibilities. Or my first toss is a tail, and then the second one is a head. These are all the possibilities if I'm tossing the coin twice and I assume it's fair. These are all the possibilities. And then I can be able to look at, I'm looking at the heads as my random variable here, my x. So x can take, if I look at this, it can take either it lands on 0 heads, which is this case, right? Or it lands on 1 head or 2 heads. So the probability that it lands on 2 heads is 1 out of 4 outcomes, which will be a quarter, 1/4, right? The probability that I get 1 head, I see it twice, here and here. So it's going to be 2/4, which is a half, 0.5. And then the probability that I get 2 heads, it's only 1 possibility here, right? Here, which is 1/4, that gives you a quarter. So it's just to show you that if x is a random variable, these are the you will have to decide what here the random variable is described to say the number of heads. So the probability that I get 0 heads is this, and so on and so on. So then we can say the probability mass function of x evaluated at 1 is 0.5. Of x being the number of heads evaluated at 0, it's going to be 1.25. And then for continuous variables, the way of summarizing the distribution is different. So and it's more complex because it's not just the probability that I get 10 heads, 0 heads. It talks about a range or intervals. Let me put it that way. It talks about interval. I've put it here, but I'm not gonna discuss it. So we can take a break here, and then when we come back, we're gonna start with the sampling distribution. Now, to just summarize, we have looked at the null hypothesis, the alternate hypothesis, which is what you have to state. And then now we looked at number 2, which is you set the criteria. You say, I will reject the null hypothesis when the p-value is less than the alpha. So we've covered what is alpha. We've covered what is the p-value. And then we looked at probability just to bring out the concept of probability, since we are using it to talk about the probability of type 1 error, and to talk about the p-value, which is also another probability that we are using. And then we will be looking at bullet 3, which is where I am, where we have to now compute the statistic. Then we're going to start to say what what is a statistic, what is a sampling distribution, and then how is it related to a statistic, and where does it come in hypothesis testing? I don't know, Tony, if there are questions at this point. It's now 10:50. So I'm gonna wait maybe to hear if there are questions. If there are no questions, maybe we can come back at 11.
Yeah, there was one question from Anonymous, and they wanted to know, okay, the question is, does this mean that I can test assumptions about the topic using a hypothesis? If I use a null hypothesis, doesn't that undermine reliability of the study?
Okay. Thank you for the question. Yes, I mean, when you are doing a study in quantitatively, and you're gonna be doing inferential analysis, it simply, you can do quantitative study, but just have a descriptive angle to it. When it has a descriptive angle to it, is you will just be describing. So from the data that you would have collected, which is sample data, you will describe the features depending on the variables you'll be. So the description talks to the sample collected. You are describing based on the sample collected. You are not saying anything about the population. You are not pasting what you are getting from this sample data to the population. When you are doing inferential is when you say that from what you are getting from the sample, you want to paste it on the population. So when you come into the study, because in inferential, there are hypotheses. So you come with a claim, the assumption that you'll be coming with. And as a researcher, the assumption, as I've said, is what you usually, it's what you want to show. And you usually want to show that something is better, things are related. You don't really want to show that things are not related. And most of the time you want to show that things are related, that this thing is different to the other. So when you put that, you don't have to put the null hypothesis in your document, right? But what I say is that when you have written it somewhere, it helps you in your mind to see where you are going. So the claim that you came with, if you say that there's a relationship between malnutrition and performance, it's a claim that you are coming with, which is what you want to test. So you will put that assumption, and I said the claim that you are coming with is usually the alternate hypothesis, so you can put it. And then it doesn't negate, it doesn't, yeah, you spoke about reliability. It doesn't take away the reliability. You said the validity, or I can't remember the word. Is it reliability? The word that is just there, Tony, is it reliability or validity?
It's reliability.
Yes, it doesn't take away any reliability. It's just saying that you are gathering data. You are doing the study to gather data evidence, to say this claim that you have. Now you are collecting data to test it so that you can have evidence to say, I am rejecting the null hypothesis that says that these two variables are not related, meaning there is some evidence to this claim that I came with, that where I as a teacher, I'm observing that there is a relationship between malnutrition and performance, because I am seeing that it looks like the learners who you know the conditions and you are able to link, but obviously you don't want to put it out there because what you're observing, perhaps you don't really, that's why you are doing the study. Yes, you have an assumption, but you are doing the study so that you can collect data which you will use as evidence to say there is something to this claim. And even we also say if the p-value obviously is small and it's saying you reject the null hypothesis, it doesn't necessarily, it can say maybe you must do a bigger study to further gather evidence towards. So you did a study and you found that there is some evidence to this claim that you came with. And then you can also maybe do a bigger study and that. But from the first study, you would be able to get a sense of this claim, that you are picking it up. So there's nothing about reliability there, because you got collecting data that you are using as evidence. At the end of the day, now what you will be saying will be based on evidence. It's no longer now based on the assumption that you came with. It's now based on the evidence as presented by the data that you collected. Yeah, I hope it makes it clear. So in terms of the what we are trying to cover today is just for you to have some understanding of where the different elements that you come across when you're doing inferential statistics, where they come in, to put in the different parts of the puzzle together, so that you don't only maybe just look at the results, you're able to have a full picture of where you're starting, why you have the null hypothesis, and how you are to see it, how it relates to the alternate hypothesis, and then to see why do we use alpha, what does it mean, and then also to see where p-values are computed from. And then at the end, then you're able to see how we arrived at the decision of whether we are rejecting the null hypothesis or we do not reject it. So in terms of the sampling distribution, it's a theoretical distribution of all the possible values of some sample statistic. So I indicated at the beginning that what we measure from the population, we say it's parameter, right? And then what we measure from the sample, we say is a statistic. So the sampling distribution talks to possible values of some sample statistic. So it's a theoretical distribution. So these are things which have been investigated and has been established that a certain sample statistic under certain conditions will have this particular distribution. So statistic will have some theoretical distributions associated with them. That is why when we do inferential statistics, you come across parametric, non-parametric. You hear that this is a parametric technique or a parametric test, because if it's parametric, then it means that there are assumptions around the distribution of the sample statistic. There are certain assumptions. So this have been theoretically established to say if we are talking about the sample mean as the sample mean as a statistic, we are expecting a certain properties or properties that are associated with them. Then this provides a frame for decision making, right? So every statistic will have its own sampling distribution. So theoretically, it has been established, and when we are doing a statistical tests, or we're doing hypothesis testing, we are using these properties or these theoretical truths which have been established about the statistics to do our tests. So if we use one example, the distribution of the sample mean. So it's sample mean, so it's a statistic, right? It's a statistic, and here when they say sampling distribution, it's all the possible values of some sample statistic. So we are talking about if we're using the mean as an example, all the possible values, so all the possible averages, meaning that this average is going back to my example, they will be coming to a fixed, they are coming from a fixed population. The example that I used, if I used the participants today as a fixed population, if I'm sampling from this population of participants who are attending. Each time I sample, I get, we were talking about age, average age, or the sample mean, which would be the age, in terms of the average. Then I sample again, I will get another one. I sample, I get another average. The average is the statistic. And here we are talking about all the possible values. So there are some properties which have been established. Like try to demonstrate using an example. So if we talk using the sample mean as an example, the sample mean will be coming from a population. The population has size n, and then has an average of mu. So I've said that when we talk about a population average, we talk about mu. When we talk about a population mean, we talk about mu. And then we also have the population standard deviation. So this population has these attributes. If I take it to this example, we know how many postgraduate students are there, or M&Ds. If we want to look at M&Ds, we have the N, which is the total. And in terms of the average age, if we get the list of all, if we can get the ages of all our M&D students, then I will have the true population average, and I will also have the true standard deviation. But now if I'm sampling, I can select the first sample, which here it's denoted by X1 bar, and it's going to be a certain value, right? So if you look at my graph, it's supposed to be symmetric. So just, yeah, I just struggled to make it perfect. This is as perfect as I could get it. So here in the center, I will have the population. This is the true one. Mu is the true one. And if I'm selecting from the population, I'm getting the estimated ones. So the first one gives me an estimate. I've plotted it here. Maybe it's going to take me here. I select another sample. I compute another statistic, which is now the sample mean. I plot it here. And then I compute another one. I plot it here. I can do this repeatedly, and it's going to give me a sampling distribution of the sample mean. So which goes to here, it's a theoretical distribution of all the possible values of some sample statistic. So for me to get, obviously, as I said, this have been studied theoretically, but when I show you to demonstrate it here, is to say you are sampling and you get some average. You sample, you get some average. You are hoping most of the averages will be close to the true value. And you will still have some extremes, right? Some maybe which are away from the true value. But when I sample, I compute, sample, compute, plot them, I will get the sampling distribution for the sample mean, because I'm using the sample mean here as an example. So it's another example here. If we have 6 soccer scores, right? So these are the scores here. I have 2, for there actually, I think there are 7, not 6, 2, 4, 6, 7. Yeah, there are 7. And yeah, it's gonna distort my calculations because my calculations. Okay, we'll see when we proceed. If you add this up and you get, so this is the real, these are the population values, right? These are the population values. They are the population values. And if I select 2 values from here, I can compute an average. So let's say I select 4, and I also select 3. So I select 2 scores here. I'm able to compute an average. the average would give me 3.5. This is if I select 4 and a 3. So I'm sampling from this population. I sample, I compute a statistic, which is sample mean in this case. And then I sample again, I compute another average, which is my sample statistic, the sample mean in this case. I can continue in this way. So first time when I select, I can get, if I use these numbers that I've put here now, I think I took out 6. Yes, I took out 6 in the computation. So we have these ones. And I'm selecting, yeah, I'm selecting 2. Each time I'm selecting 2. So you will have a sample size, right? And for you to be able to look at the sampling distribution, you will be selecting the same way, the same number of units. So my population has 6 scores. You can see them, 6 scores. If I'm selecting 2, I can select what? A 1 and a 1, right? Which is where I am. I wanted to get to the... Okay, I wanted to get... Now I can't access my... what do you call it? The pointer. So, but I hope you will see with the cursor. So I can... First time I can select a 1, and the second time I can select a 1. Or I can select a 1 and a 2, right? A 1 and a 3, a 1 and a 3 again because I've got 2 3s, or a 1 and a 4, or a 1 and a 5. Same way, I can select a 1 and a 2, a 1 and a 3. So these are the possible samples I can have. These are the possible samples. And when I select a 1 and a 1, my average is going to be what? It's going to be 1. The mean is going to be 1 because I'm going to say 2 divided by 1 plus 1 divided by 2 will give me the average of 1. If I select a 1 and a 3, it's going to be 1 plus 3 divided by n. It's 2. It gives me 1.5. If my sample has 1 and 3, then I'm going to have again an average of, I'm going to have an average of 2 because it's going to be 1 plus 3 divided by 2. It gives me a 4, and so on. So these are the possible averages, all of them for my population. Remember, my population here is 6 scores, and I'm using it so that it's a small number that you're able to see. So these are the possible averages, all of them. These are the possible averages. These averages, they actually give me, from this I can get the sampling distribution of the sample mean for this population. We know that the average is 3 because I computed it here, that the average is 3. That's a true one. The average of this, the possible values of the population is 3. And these are the ones that are inside the table are the ones computed from the samples of size 2. Then I can also now do a frequency distribution to say how many samples gave me a sample mean of 1. I only had 1. That's when I select a 1 and a 1. I get a sample mean of 1. And then from this, how many samples gave me an average of 1.5? I have 2, this one and this one. And then I can also look at how many gave me 2. Then you can count them here. You create this frequency distribution. And then you now get the probability. What is the probability that if I sample 2 from this population, if I sample 2 scores, what is the probability that it's gonna be the average score will be 1.5. I get to this probability because I only have 2 out of this possible 36 outcomes. 2 of them gave me an average of 1.5. What is the probability that when I sample, I get the 2 scores that I would have sampled, they give me an average of 2. Then I have 5 occurrences where the average was 2, 5 cases where the average was 2 in terms of the probability. So you can compute for all of them. The highest was 5 here. The highest sample mean was 5. So you can compute, then you have 1. And then you can see now you have these probabilities, and you can see that 3, the ones that are close to 3, you've got a lot closer to 3, which is the average. You've got quite a lot of them there. And then you have some which are far from the population average of 3. So this would give you a sampling distribution. This is how you compute a sampling distribution. It's all the distribution of all the sample averages. If I'm talking about the statistic as in the sample mean. So it's associated to a certain sample size. If you look at the definition, it's going to be the sample that are drawn, possible values of some sample. That sample will have to be consistent, right? If you are selecting 5, it's 5. If it's 30, it's 30. Then from that, you are able to construct your sampling distribution. And here we are using these 6 values to show you how you get from the population observations. So these are the observed values there, and they are population because it's everything. These 6 scores are everything. It's all the matches that they've played. And then now I want to see, using this information, maybe I'm just going to select 2 games, and then I'm able to use that to compute the distribution. And you can plot it. So you can see it said this would be the sampling distribution for the scenario that we've looked at. I have all the possible averages for all the possible samples of size 2 I can get from that data. These are all the possible samples of size 2. We said I can have 36 different different events, which would be like, it's either I get, if we come back here, yes, different possible, the average is a 1, a 1, a 1, a 2. These are my possibilities for the observations. Then they give you this sampling distribution. You can plot it. As you can see, most of the observations will be closer to the true value here, and you still have some on the extreme. So if I was making a hypothesis, my hypothesis would be around the population, what is true about the population. So here my population is the scores. If I were to make a hypothesis, it will be based on what I know to be true about the population of the scores. So I'm going to proceed for the sake of time. So this is another example. Here we're going back to our a coin. If we toss it 3 times, right? Now we are tossing it 3 times. These are the possible outcomes. A head, and a head, head, tail. These are the possible outcomes. The first time I can have this head, head. So these are I have 8 possible outcomes. And then if I'm looking at the heads of getting 2 heads, then I will be looking at the outcomes where I have 2 heads. And I can see I have 3 of them, and each one with a probability of 1 out of 8. Then I can compute this probability. And then we going back to what we covered, the probability of having 3 heads, I can also compute it. It's when I have this pattern. So I can look how many times do I have that pattern. The probability of having 1 head, I can look at how many times I've got that pattern. The probability of having 0 heads, I can also look at that pattern. And from that, I can be able to also do a distribution. If I'm looking at heads, then I can either have 0, 1, 2, 3. So you can see also I can compute some distribution, and I can see 0 heads, 1 heads, 2 heads, 3 heads. I'm able to get some distribution. And this is, it's gonna cover everything. These are all the possibilities. That's why I am getting the distribution here. So just to wrap it up, if it's 10, if I toss 10 coins, then I can also look at the sampling distribution. You can see you have now outcomes that are likely and those that are unlikely. And you can see that it's 10. If it's balanced, your hypothesis would be around that you're gonna get 5 heads. And then you see that most of the outcomes are close to that. Then you have those ones that are on the extreme. That's why when we talk about the null hypothesis, is that if the null hypothesis is true, then you will find that most of the observations will be close to this. And then the extreme will be thinner. But if the data is not supportive of the null hypothesis, then you'll find the tails will be here, they will be a little bit thicker. So in general, we can determine the sampling distribution of different sample quantities constructed from the data of random samples. Then we call them sample statistics. So we have said that each statistic has a sampling distribution, and there are some properties which have already been established. I've already shown you have seen that with the examples that I was showing, is that as you sample, when we talk about the average, as you sample, these samples, they are these samples, they form a bell-shaped. That's what you should have seen, a bell-shaped there. So that's one of the properties. Obviously, if the data is skewed, then as you sample, they will not be forming this this bell-shaped that you are seeing. And that is why when we talk about the parametric tests, we talk about assumptions of symmetry, because theoretically it has been established that when it comes to the sample mean as a statistic, as you sample from the population, as you do many samples, they will take the form of a bell shape. That would be for large samples. And then we can also have the same for your standard deviation, your variance. And we will be using them, obviously, the sample mean, and this we are using them to estimate population parameters. So the mean will depend on the sample that is selected. So the sample mean can be the random variable, and then it's going to have a distribution, a probability distribution. Yeah, so just to summarize also about the mean, our knowledge about the distribution, that we know that the distribution of the sample mean can be symmetric, then it enables us to know how we can use the sample average to estimate the population average. Yeah, so we have different sampling distributions for different sample statistics. So they have been established. So when you talk about the mean, you will see, we will talk about a t-distribution. And when we do statistical tests around the mean, we will be talking about a t-distribution. So these are some properties which have been established, and it is known when you say a t-distribution, it's got a certain form, because theoretically it has been established that when you sample, as you sample this mean, you sample and you compute the mean, sample and compute the mean, you get a certain distribution. So this ties in also to the concept of the central limit theorem. I don't know, some of you might have heard it, but these things, especially around the mean, they're important because most of the analysis that is done, a lot, let me not say most, let me say a lot, is around the mean. Because once you collect data on continuous variables, which I will not explain because we've covered extensively in previous workshops. When you collect data on variables that are continuous, how we summarize them is we would summarize them using the mean. And we are using the mean because we also assume that that variable would be, if you were to look at its distribution, it's going to take the form of a bell shape. However, there is also, in addition to that, even though sometimes when you plot a continuous variable, you might find that it deviates from that bell-shaped distribution. We also have the central limit theorem that tells us that for large samples, the sampling distribution of the mean. Remember, here we are talking about analysis that is centered around the mean. The sampling distribution of the mean will approach a bell-shaped. So even though the distribution of the variable is not a bell-shaped, but the sampling distribution of the means that are coming from that population, the different means that you compute from that population will approach a bell-shaped. So roughly, this means that a histogram of the actual random outcome is quite similar to the theoretical histogram of the potential outcomes described by the population. So you have the random variable, and then you have the theoretical properties. So when you have large data, we take it from the central limit theorem that in terms of when we are looking at averages, that particular variable, their distribution is going to approach a bell-shaped, even though the individual observations do not resemble a bell-shaped, but we know that the sampling distribution of the mean will approach a bell-shaped, and as such, we will treat that variable to be symmetric. Yeah, for you to, the concept of symmetry, I didn't touch on it here because we've touched on it in the previous workshops. So if we go back to the central, so this is a symmetric distribution, right? How you see it is that if you were to slice it in half, the two halves will be more or less the same. Sometimes we say approximately symmetric, approximately normally distributed. So when I'm talking about symmetric, I'm talking about this. And you can see that as I was plotting those sampling distributions that I used in the examples, they give you something like this. So this is a symmetric distribution. And we use these properties. These are used in hypothesis testing because the theoretical properties are used now to say, to compute the p-values. We know that, as I say, that if it's symmetric, the two halves will be identical. As such, this red portion here and this red portion will be equal. This and this will also be equal. So if we say that a distribution is normal, then these are some of the expectations. The numbers, they are they vary slightly depending on the source that you are using. I mean, this, for example, in another source, you're gonna find exactly 95, not 95.4. Yeah, just a caution that there's a slight variation in terms of these percentages, depending on the source that you are using. But we know that once we say that the distribution is normal, then these are the attributes that we are expecting. For instance, we are expecting that 2.1% of the values will fall below mu minus sigma, right? And then 2 between sigma minus mu minus 2 sigma. Then we also know that, for example, 34.1% of the values here, the green part, will be between mu minus sigma, just here. The average minus 1 standard deviation, or the average plus 1 standard deviation. So these properties, once you say it is symmetric, these are some of the things that we will be expecting. So in practice, the shape of the actual and the theoretical distribution are compared using graphs. So yes, so you'll have, this is a theoretical, what we know, and then we have data, and then we will take what we are seeing from the collected data, and we'll be comparing it against the theoretical to be able to see if it's symmetric and the deviation from symmetry. So in simple terms, what the central limit theorem is telling us, whatever the probability mass function or the PDF of a variable is, if we randomly select a large number of independent values from the random variable, the mean of those values, if collected repeatedly, will have a normal distribution. So that's what I'm trying to say. If you look at this, here you have the original distribution in red. This is the distribution of some random variable, But we are saying that if we select many samples, then we know the central limit theorem is telling us that the distribution of those samples will have a normal distribution. So it's important because we use it when we talk about assumptions in hypothesis testing. And these are things that are centered around the average. So once we use the central limit theorem, we are saying when you have a large sample, then even though there are deviations from asymmetry, but because of the central limit theorem, we can say that there is convergence to symmetry, even though the original distribution was not symmetric, if you see this. But the central limit theorem is telling us if we sample repeatedly, the samples will converge towards a symmetry. So if we go back to the example of the scores, we assume we have a large number, 150 instead of 6. And then if we select now, we're selecting 2, now we select 40, and we compute the sample means. Then according to the central limit theorem, the histogram of the sample means, remember, we select 40, 40 scores, we compute the mean, select 40, compute another mean, another 40, another mean. Then what we are saying, the histogram of all the sample means will show a normal shape, even though the original scores might not have been normally distributed. So this 150 might not have, if I plotted them, I might not have seen a bell-shaped. But according to the central limit theorem, if I select a large number repeatedly, and I compute the averages, the distribution of the sample means will show. So that's why we sometimes say when you have large data, even though when you look at the variable, sometimes it is not symmetric, but using the central limit theorem, you can treat it as symmetric once we say it's symmetric, it means that we can use the statistical test. I think maybe the importance of symmetry is that when we say it's symmetric, then it means we can use the parametric approaches, which are the approaches which are centered around the mean. And the mean is a measure of centrality. And then it has to be central. Once the mean is not in the middle, that's when we talk about asymmetric distribution. But then the central limit theorem is telling us that for large samples, we know that the sample means if we sample repeatedly. So this is something that has been proven theoretically, right? When you are doing your analysis, you're not going to be able to do this because you don't have the population, you only have the sample. But theoretically, it has been shown that even though the original distribution might not be symmetric, if you were to sample from the population where the observations came and you sample many samples, they will converge. That's why when we have large samples, we will say treat them as symmetric, but you always apply your mind there. There are some variables that even if you have a very, very large sample, you'll still treat them as not symmetric. So just to show the central limit theorem, what it's capturing there. So this is symmetric, right? This is what we mean by symmetric. And this is skewed. And then these are other ones. So you can see it's now talking about large. So once the sample becomes large, the guideline is, when it says large, most references, they talk about sample that is greater than 30. But even there, you can use other pieces of information to make a decision. So what it's telling you is that this was the original. You can see it's not symmetric, right? But the samples that will be drawn from the population where this variable is coming from, if you select, they will approach symmetry. You see here, you see what is plotted here. It's the sample averages. So the central limit theorem is telling us that for large samples, the averages that you will be getting from the 30, as you select 30 plot or 50 plot, it's going to approach symmetry. You started here, but now the central limit says that the distribution of the sample averages approaches symmetry, which is bell-shaped like at the bottom. Then it says that we can treat that variable as symmetric. So for large data, just to say it again, when we apply the central limit theorem is we say, even though when I look at the variable, it might not look symmetric, but based on the central limit theorem, because I know if I had the opportunity to do this, it will approach a symmetric distribution, then I'll treat the variable. But also caution is needed because you need to be able to say, use your other pieces of knowledge. As I've said, there are some variables like income in a very like an equal society like South Africa, where you wouldn't treat income and analyze it as an average. You would really treat it as a skewed variable that it is. So yeah, to find the mean and the variance of a sampling distribution of statistic, it's easy. What is difficult is the shape of the sampling distribution. And the central limit theorem enables us to predict or approximate that shape. And once we know that shape, then we are able to, the shape talks about how that distribution would look like. Then we are able to know if it has this shape, then it's going to have these properties, and then we can use this in hypothesis, those properties, because it has this distribution, it's got these properties, then we can use it for hypothesis testing. So in terms of the distributions, I showed you the example of the discrete. The continuous there is some information in the slides which I didn't cover, but they are fully characterized by their probability density function for the continuous and the probability mass function. In the notation section, so you will see in the different textbooks, they will use this delta is to say that that variable is distributed as. And I've explained that here it says, what does it mean for a random to follow a certain distribution? Fully describe the probability of events for that random variable. So when it follows a certain distribution, it means that it's a PMF, which I think the PMF I did show some examples. It shows that PMF of that distribution fully describes the probability of events for that random variable. When we are performing data analysis, theoretical distributions that we think we will approximate our measurement for the population from which our sample was drawn is usually chosen. So there will be theoretical distributions. As I said, if we know I'm dealing with the average and I know that this I'm assuming that it's got this theoretical distribution, then I can use the properties associated with it for me to be able to do the statistical test, select a statistical test. Assumptions associated with each distribution. So here, mostly it's about symmetric because it's around the mean. When we talk about symmetry, mostly we talk about the mean. And then when we talk parametric, it just means that we are making assumptions. So there are some known assumptions that we are making. They don't necessarily have to be about the mean, but it can also be assumptions about certain quantities. But when we say parametric, mostly it means that there are assumptions. And when it's non-parametric, it means the statistical tests are done without making assumptions about the distribution of the data. So there are a family of distributions that have already been theoretically established and proven. So once I say my data is like this, then it means I can choose from a family of those distribution depending on what I say the distribution of my data is. And then once I say that, for example, if I say my variable is normally distributed, maybe it's weight, then I'm using maybe the t distribution because I'm doing something around the mean, the average weight. Then I can always check afterwards if my assumption to say the weight is normally distributed. So I can do my analysis and then afterwards I can check if my choice of the distribution was good. So that's why when we do data analysis, we'll do data analysis and then we assess to see if what we are getting is in line with what we are expecting. So we need to check. Once I've done a t-test, I need to just check the residuals and see. And then I can be able to change sometimes to another distribution. So I'm just going to touch on some common distributions, the ones that perhaps maybe you will be able to connect with. Yeah. So binomial distribution, it's about discrete variables. So discrete also we've covered in previous workshops to say when we say a variable is discrete, what do we mean? So binomial distribution is a discrete distribution that represents the number of successes in independent trials, each with a probability of success of p. So all the different values of n and p define a whole family of different binomial distributions. So the outcome of a random variable that follows a binomial distribution is a whole number because it's discrete, right? When we are talking about an outcome that follows a binomial distribution, that outcome is going to be a whole number. It's going to be a 1, a 2, a 3, a 4, a 5. It's going to be a whole number. That's an outcome that can follow a binomial distribution. If our n is 1, it is called a Bernoulli. So these are the parameters of a binomial. It's going to have n. N is n as in the number of the trials. P will be the probability of success. Let X will represent a particular outcome. That outcome will be a number between 0 and 1. So you can use this to say what is the probability that the number of heads will be 0. So X will represent, the big X will represent the random variable number of heads. Then the specific outcome, the number would be the small x. Then this would be the... So with a binomial, there are two possible outcomes, like a yes or no. So we talk about or success or failure. I think as you saw, we look at success or failure. I regard this as a success. You can define what success is, right? Success can be the number of heads. Success can be the number of defects. So if I'm looking at that probability, it doesn't necessarily, you have to see it as a yes or no, but you can define what success is. It's just that the outcome, you have success, and the other variable is the opposite of success, which will be failure. So as I said, success can be the number of heads in the context of the examples we've been using. Success can be the number of positive COVID-19 cases. That would be a success in that example. The other ones would not be success. I'm now rushing because of the time. So we know, so these are some theoretical properties. We know that if we have a binomial distribution, the theoretical mean. So these are theoretical properties. Once we say it follows a binomial distribution, then we can now also know that the theoretical mean will be the number, the sample multiplied by the probability of success. Then the variance, we can compute it mean. So it means that for a certain sample, the sample mean and the variance will be similar to the theoretical values. And the larger the sample, the more sure we are that the sample mean and the variance will be close to. So for large samples, then the sample mean and the variance will be close to this theoretical properties. And we also know, so this, I'm just showing you this. So when we do statistical testing, we tap onto these properties which have been established. That's why they will say when n is large, then we'll say even the variable is a binomial and it's going to approximate a normal distribution. So this is an example. So suppose that 60% of all first-year students pass this module. So if we take, so we know this is what we know. If we sample 50 first-year students, n is 50. So what is the probability that exactly 40 students will pass? So here, success is a pass, right? So we want the probability that 40 will pass. The probability of passing is 60%, 0.6. So then you can, because we know we are talking about pass and fail, which is which we can say it follows a binomial distribution, then we know we can use what has been established to compute this probability, which you can compute by just plugging in the numbers. 50 is n, success is 0.6, 60 converts to 0, n is 50, and then the x, which is the number of the successes, is that we are looking for is 40. Then you get this probability. So we have this probability that 40 students out of the sample, 50 will pass the module. This is just more information to understand the formula. So I used the binomial distribution as an example of the known distributions. Now I'm using the normal distribution. So with the binomial, we're talking about discrete, and we are talking about they can assume whole numbers, 0, 1, 2, 3, 4. With a normal distribution, in its truest sense, we are talking about continuous variable, which is symmetric or bell-shaped. We've seen a bell-shaped. And then the family of this distribution will have two parameters. We have a population average and a population variance, or a standard population standard deviation. The support is all of the real numbers, but the tails are very thin. Yes. So we know that one of its properties of this distribution is that the probability that X is more than 4 or 5 standard deviations from the mean is extremely very small. If you look at that, the distribution that I used here, yes. So if it's a normal distribution that we have 4 standard deviations from the mean, here you see it's 3 standard deviation. The probability that we have here, 4 and 5, it is very small. Not to say that we can't, but it's very small if a variable is continuous or normally distributed. Yes, so then we will so yeah, for the normal distribution, just to wrap it up, it's continuous. A variable would be continuous, symmetric, right? Meaning that when it's symmetric, that the values are close to the mean, and then the extremes are thin. So the tails are very thin. It's gonna have a population average and a population variance or standard deviation. So going back now to our decision rule, we said we have the null hypothesis. We said that we have type 1 error. We spoke about alpha, which we used to reject. We reject the null hypothesis when our p-value is smaller than the type 1 error. And then we said the next step is to look at the test statistic. The p-value, even though we've explained it, but we haven't computed it. So the p-values will be tied to our test statistic. So in terms of our decision rule, we say we compare the computed p-value to a predetermined value alpha, right? Alpha, we set it as 5%. So it's a predetermined value. You do a statistical test having already set the alpha, and then the p-value will be computed. The p-value is computed. It's linked to the the test statistic that you will be using. So we say if the p-value is less than alpha, we reject. If it's greater, we don't reject. And we see that they say you must be greater than 0.5 because Mugai fails to reject the girl. So just tying it in with an example, the different pieces. So the example that I will be using is the t-tests. So the t-tests are based on what? Population means. I think I've said that. So when it comes to the t-test, they are evaluated through t-values, t-distribution, and degrees of freedom. So these are the properties around the sum through which the sample mean is evaluated. We have 3 types of t-test. So they will depend on what you want to test. This test will be dependent on what. So if you have one sample, for the example was when we had, yes, in the workshop, we used the example of the weight, right? The weight of the newborns, to say if we hypothesize that they are a certain value, the average weight is 3.5, this would be a one sample, because I have a sample of newborn babies, and then I'm going to be measuring their weight, and I'm going to compare it against the hypothesized value. Then we have two independent sample t-tests. That's when if I say I have two treatments that I'm comparing. So in terms of my sample, one group will receive a new treatment, the other group will receive a standard. And then I'm going to compare the average marks. So the average marks of the learner, the students who got a new teaching approach. So then I would be doing an independent sample t-test. I have two samples and they're independent because those who are getting a new teaching approach are not the same as the ones who are getting the standard approach. So those two samples will say they are independent. Then I can have dependent samples, right? Whereby now we go back to the example of the blood pressure. I can give, so I have the same group of patients. I take their measurements before I give them a treatment and after. So it's the same sample. I have measurements for before. It's a group of measurements. Then I also have measurements for after, which will be another group of measurements. Then I'm comparing the averages, then would be dependent because the people who were measured before is the same people who were measured after, so they are dependent. So in terms of the one sample to test, I can use it to compare the population mean if it's equals to some hypothesized value. I have one continuous. So I'm assuming, so now when I tap into the theoretical distribution, I'm talking about a mean, so I'm assuming that the weights would be, once I assume they are normally distributed, it means that I can use the properties that are associated with me making that assumption. So the null hypothesis, as I said, will be mu, which is the population is equal to some value, right? Then I'll have the alternative that says it's not equals to, or if I'm doing a one-sided, I can say the population is greater than some hypothesized value or less than. So because I'm assuming that the distribution is normal and I have one group, then I can use what has been established. So the test statistic then will be a T, a distribution, and this will be the formula. So this is what happens. Once you say for the mean, once you say I'm treating it as parametric, it means you are saying that you are treating it as normally distributed. So even in SPSS, once you select the t-test, you are saying that you are invoking those theoretical properties. Those theoretical properties will be invoked. And as such, this will be the test statistic that will be used. So when you get your results, they will be based on this test statistic because you made a certain assumption about your data. And yeah, the section about the sampling distribution was to show how you get to the sampling distribution. And then once you say it's got this theoretical sampling distribution, as I say, then you can tap into the test statistic associated with that distribution. So for one group, you will have this, and this is what you will use to get to your p-value. You will be, so there are several ways to compare. So you can use, there are tables if you look at statistical textbooks at the end, but even if you search, you will find tables. So if you say the test statistic is a T, you can look at the table for the T distribution. And once you've computed the T, you can take the value here, and then you can also take the degrees of freedom. The degrees of freedom, it's about the number of it's about the number of the information that is allowed to vary. So here, there will always be the degrees of freedom. It's also one, I think, in the when I introduced the part about the t-test, it's one of the things that you'll be using to describe the distribution, that it's a T distribution with certain degrees of freedom, then it's going to have a certain shape. So the degrees of freedom for a one sample test will be n minus 1. If you have 20, the degrees of freedom will be 19 minus 1. And the degrees of freedom, maybe how to understand them, as I've said, it's the independent values that can vary. So if you have, for example, 5 observations that you sample from a population, those observations, they will have values associated with it. So if I'm sampling scores, I will have 5 scores. Those scores are each a value. They are each a value. So whatever you're sampling will depend on what the values are representing. I'm using, if I use the scores, each of the 5 scores is a value that is representing a particular score that was observed. So if I want to, if I use the values to compute the average, I will use all 5 of them to compute the average. And I can sum them. That's how you compute the average, and you divide by n, right? But what you need to know is that if once I get the sum, which let's say the sum is 40, let's say the sum of them is 40, I can still arrive at 40, the sum of 40, by changing, I can still change 4 values and still arrive at a sum of 40. And only one value I cannot change, because once I've changed the 4 values, the last value will have to be a number that ensures that I still get a sum of 40. So that's what we mean by the independent values that can vary. So if I just go back to it, I know we are out of time, is I have 5 scores, and then maybe I want to compute an average. The total number of scores will still be 5, right? And then, but if I compute the average, it means I sum all of them. Then if you look at it on the other hand, is to say that I can change 4 values there, and I can still have the same average by making sure that the last value, I don't have room the last value will have to be a number that ensures that when I have changed any of the values, this last one will have to be a value that will ensure that I still get the mean of 40. That's what it means. So that's why even with the sample standard deviation, we don't divide by n, but we divide by n minus 1. We divide by the degrees of freedom. So the T and the degrees of freedom, then you can be able to go into the table and look at the distribution. If you are doing it in SPSS, it's going to compute this T and then use this to be able to give you a stat. So if we go to this will be the last part. I'm wrapping up. So if I go back to my example about newborn babies, so if you assume that smoking affects the weight of newborn babies, so we hypothesize that the average weight of babies at birth is 3.5. So obviously this is a theoretical figure or something that is known to be the truth in that space. So if I have a sample of 22, so I collect data, right? Maybe it's going to be, it can be secondary data, meaning that I can go and request for secondary data. And then hopefully, obviously, the data will have to have a state, it must say whether you smoke or you don't smoke for me to be able to do this analysis. If the secondary data doesn't have that, I'm not able to use it because I need to be able to identify the mothers who smoke from this secondary data. So let's say I find I have 22 mothers who smoke, and then I find that when I look at so this one is the hypothesized one. This is what we believe to be the population value. And then X bar is the one that I will compute from the weights of those children who are born by these mothers who smoke. Then I can also have this. I think it's supposed to be a standard sample standard deviation, not sample variance. So it's, yeah, without the X. Then my null hypothesis in that case will be mu is equals to what? 3.5. So the population, I'm saying it's equals to, I'm hypothesizing that it's going to be 3.5. So the data from this sample, I'm using it to estimate the population. So I'm going to see if this, based on the data, if I can say it's equals to 3.5, then because it's you see, then that's when now you go to the theoretical distribution. Because I'm assuming that the weight the weight of these children, these babies, is normally distributed, then I will use these properties. Then I can compute the T in this particular way. If I don't assume that it's normally distributed, then I will have to compute the test statistic using another formula, which will be non-parametric. So because I'm assuming that a certain distribution, then I'm able to tap into what has been established. Then I'm able to specify also the degrees of freedom. So here, the degrees of freedom is going to be what? It's going to be 21, right? And then I can compute the T. And then I can be able to go and look at the table to see for this T and this degrees of freedom of 21, testing at 0.05, what is the p-value? Then I'm going to be able to get to the p-value. So this is how the SPSS, this is what is happening in the background. So similarly, if you are doing independent samples, it's a t-test. If you assume symmetry, that it's normal data, this will be the hypothesis will always be there. It will be around the mean. And then you can now tap into with us what is going with your assumption is those the theoretical distribution. And then you can be able to now use the test statistic for independent samples. And then you'll be able to get your T distribution. And then you can look at the distribution. You can get the T statistic, which will be a value, as I showed you here. You'll compute it by populating. So even here, you'll populate the things for the one group, which is the X, the other things for the Y group, the X and the Y group, the size of the X group, the size of the Y group, the two groups that you are comparing, and you get your T statistic. And then you are able to also put in the degrees of freedom, which now becomes, you have two groups now. So you have the total for the two groups minus 2. And then using this information, you can go to as I say, a table with for a T distribution, and you can be able to get the p-value and make a decision whether you reject the null hypothesis or you don't. If the p-value is small, then you will reject the null hypothesis. If it's not small, you don't reject the null hypothesis. That's the decision, the criteria we've put. So how everything fits in together is obviously you start with a research question. And then from it, as I've said, you formulate a null hypothesis and alternate hypothesis. So with the research, you'll have a hypothesis. The alternate hypothesis will be what you as a researcher want to show. Then you can take the opposite to make the null hypothesis. Then based on the hypothesis, then that will tell you whether the design, what the design should be. Should the design be an experiment, or should it be an observational study or a quasi-experiment? So the hypothesis and what is available, I think, will lead you to here, will lead you to the design that you will be able to follow. Because you will have a population that's where this thing that you are interested in is occurring. And then you would have selected a sample, and then you have the results. So, for example, if I go back to the example of if I wanted to look at the relationship between malnutrition and performance, I cannot do an experimental design, right? Because I will not be able, you cannot subject children to malnutrition, right? So you can see how the pieces also come together. Because I want to look at the relationship between malnutrition and performance, how they are performing in class. Here, the hypothesis also is helping me to make a decision. So because I have malnutrition, which I cannot approach it from an experimental point of view, it means that it's something that I will have to be observing, right? I'll have to just observe it. I'll have to ask several questions. So from all the children, I will ask certain questions to measure malnutrition. And then I'll also measure their performance. And then I'll be able to correlate the relationship and be able to see, am I seeing a relationship such that where there is where there is malnutrition, you see that the performance is low. Yeah, I hope you see what I'm trying to explain, to say that the hypothesis also will help you with a design that is appropriate. And the example that I used, I think, makes a sense because you are able to see that certain hypotheses can only be tested using certain designs. And then because you are also aware of that, in your sample selection, you will accommodate that. Then you have your results. And then based on the sample, the variable that you are collecting, you're able to use the right theoretical distribution, right? And then you can be able to compute the T statistic, yes, as you saw. Once here I have a variable, obviously these sample results are for a certain variable. Then based on this variable, or the assumptions I'm making about this variable, I can select a T statistic. So I used the example there that we selected a T statistic for one group. So even here, I will select the right sample statistic. And then from that, I can be able to use that together with other information, for example, the degrees of freedom, to get the p-value. Then from the p-value, I'm able to make a decision to say whether I reject or I don't reject the null hypothesis. Yeah, I did rush through some sections, but I hope it still made some sense. And I apologize for the extra time that we went through. I'm going to pause here, Tony. Thank you.